billions and billions and billions of numbers. Only 5 groups to stick them in? What do we do? Oh, look, there's a 6 in the box. This time, only math matters. Let's go. What's good, everybody? Teacher Time back with you. We're diving into 7th grade. This is the first lesson on set of standards for the 7th grade curriculum. You take a look here. They want us to compare and order rational numbers expressed in various forms using the less than, or greater than, or equal to, and recognize general equivalent representations of rational numbers, including equivalent fractions. There's going to be a lot more work on fractions to come, so we won't do a lot of that, but I'm just going to show you a little bit of the number line and how to compare the numbers. What I will do and spend most of the time on is classifying numbers into one of 5 groups, that being counting, whole, integer, rational, and irrational. Let's dive into it. All right. So these are the boxes that I was referring to at the onset and a little bit earlier in the series. Now, every number can be classified into one of these boxes. And as you can see, 4 of the boxes are contained within each other, kind of like the Russian babushka doll, where a doll has a doll inside of it, which has a doll inside of it, etc., etc., etc. So, we're going to start from the innermost box and work our way out. Excuse me. Again, we're going to start from the innermost box, the black box, and work our way out. And I had to use the thumb drive to bring this page over, and I forgot to take that text box off of there. So if you kindly ignore that, I guess I will too. Excuse me. Sorry. So let's get into it. Now, the boxes are inside of each other because the number of numbers that's in the box is smaller as you go towards the center box. By that I mean the black box has the fewest numbers in it. Those numbers are also contained in the orangey looking box, but we're going to add some more. And the numbers inside the orange and black box are contained inside the green box, and the numbers inside the green, orange, and black boxes are all contained inside the blue box. Now, the cyan colored box has no numbers that are associated with the 4 boxes here. You'll see what I mean when we fill in the numbers here. So, I do have it kind of color coordinated here for the counting numbers. That is literally how we count. Right? 1, 2, 3. I'm going to put a dot, dot, dot here. 1, 2, 3, 4, 5, 6. Just literally how we count. Now, that box in and of itself seemingly has an infinite number of numbers because, and you've probably done this as a young student, even as an adult at some point in time, where it's come to some kind of contest and somebody brings in the I word, infinity. Well, I have this. Well, I have this. Well, I have this much. I have this much. I have this much. Well, I have infinity. Well, infinity not being an actual number, after some number before another number. It's more of an idea because you can always add another number to infinity. And you have infinity plus 1, or infinity plus infinity, or infinity times infinity, or hang on to your hat here, infinity to the infinite power. So there, just this one box, the smallest box, has an unholy amount of numbers in it, and it's the smallest box. And I said that we're going to be adding numbers with each bigger box. Thankfully, when we go to the orange box for the whole numbers, the only number we're going to add is 0. The only number we're going to add is 0. Those are whole positive numbers. It's all the numbers from 1 to infinity to the infinite power. The only number we're adding is 0. Just as the whole number. And by whole number, I mean not 2.3 or 3 4/8 or 0.625, something like that. Those aren't whole numbers because we literally have a piece hanging off to the side, be it a fraction or a decimal. All right, real quick there. So the green box. All right. Now it gets kind of tricky. The green box, the integers, the only thing they add to it, and it's a lot, is the negative numbers. The only thing the green box adds is the negative numbers. Because remember, in an earlier, maybe the first, and I keep going back to earlier episodes, you might want to get used to that because math is always great when you can pick up something from before. Now, I know this is the first episode for the 7th graders. Hey, looking on 7th grade, the 6th grade curriculum. Never hurts. But in that 6th grade lesson, I said that an integer is any number, and we'll call that number R. The opposite of that number, which we'll call negative R, and 0. So 13, negative 13, and 0. Negative 5, integer. The opposite of negative 5, which is 5, and 0. So we've added 0 with the orange box, and now we've added the negative numbers with the green box. And now we have an uber infinite number of numbers here at the orange box. Now we're going to add even more numbers to it. Because the only numbers we don't have left are those that aren't whole, that are integers. They are integers. So 0, 1, 2, 3 are in there. They are counting numbers. So 1, 2, 3 is in there. They are integers. So negative 3, negative 2, negative 1, 0, 1, 2, 3 are in there. All these numbers in the black, orange, and green boxes is in this blue box. But now we're adding numbers that aren't whole. And the rational numbers has a kind of spiffy definition. And a lot of the times with my definitions, you won't find them in the book, and you won't find them on page 32, and it won't make you write it all out and all this. If you can take this little nugget of information and remember it, it'll help you going forward. One of those little nuggets is in rational numbers. A rational number is quite simply an answer to a division problem. Now remember, I said a fraction is a division problem. So let's take one number that we see in each one of these boxes here. Let's take the number 3. All right, we see the number 3 in each one of the boxes, black, orange, and green. Excuse me. Is 3 a rational number? Well, it is, so spoiler alert. But let's see. Is 3 an answer to a division problem? Well, just off the bat here, 9 divided by 3 is 3. And what about this negative 3? Okay, well, let's make it negative 9 divided by 3. That is negative 3. So, that's how every whole number is in the rational numbers box. There's a couple of extra types of numbers, though, and one of them is kind of easy, one of them isn't. Decimals and fractions and pieces of numbers, kind of the opposite of the orange box. Remember, the orange box was whole numbers, 8, 9, positive whole numbers, not numbers with the piece hanging off of it. So a number like 4.5. Number like 4.5, that's a rational number. Well, is 4.5 the answer to a division problem? I'll say it is. What is 9 divided by 2? It's 4.5. Now, things like that are in the blue box. So we've added the counting numbers 1, 2, 3, 4, 5. We've added 0 to it. Then we've added the negatives to it. And if you imagine that number line, I think I got a number line on the next page here. We're stretching out to the left. We're starting at the number 1 with the innermost box. We start with the number 1, 2, 3, 4, 5, the counting numbers, how you count. When we did the whole numbers, we stretched it to the left to the number 0. And then with the green box, the integers, we stretched it a bit further to all of the negative numbers. So now we have from negative infinity to positive infinity as far as whole numbers. But there's numbers in between whole numbers. Name a number, and this is another weird exercise. We said that the innermost box has an infinite number of numbers, and that's true. So when we added 0, we've got an infinite number plus 1 plus 0, right? Plus one more number, let me say, the number 0. And then when we added the integers, which means add the negative numbers with the integer box, we added the negative whole numbers. So this infinite number of numbers in the black box has had 1 added to it, and then had the whole another infinite number of numbers added to it. So this infinity thing is kind of fickle. You can't really nail it down. It's not like 17. Oh, okay, it's between 16 and 18. It's prime. That means you can only multiply it by itself, etc., etc. Not only that, but zoom in on this one, 7th graders, because we're going to hold on to your head here. I know this is the first lesson, but the things I can tell you now, if you hold on to them, and now that they're in this video, you'll hold on to them to time indefinite, it'll help you out here. Let's just, on this kooky number line here, just doing a little bitty number line here, just a little piece of a number line. Let's say, not the whole big old 30 to negative 30 and all that. We're doing that just 2 to 3. Obviously, one number away. Now that we're doing decimals and obviously fractions, because remember, number 1, a fraction is a division problem. We take the top number and divide it by the bottom number. So there you go. When I say the blue box is an answer to a division problem, we see that that answer to a division problem could be a whole number, 9 divided by 3. It could be a negative number, negative 9 divided by 3. It could be a decimal, 9 divided by 2. It could even be a fraction, 3 divided by 4. If you could imagine baseball, you got 3 hits and 4 at-bats, then you got to hit 0.75. If we get to percentages, we drop that decimal and move the decimal 2 spaces to the right and add a percent. So 0.75. So all these numbers in the blue area, inside the blue box, are rational. So now zoom into the number line that I wrote here. Just a little funky little number line with 2 to 3 on it. And also remember, it was a little bit ago that I said that the smallest box, the black box, has an infinite number of numbers in it. So it keeps growing as we zoom out from black to orange to green to blue. Let me ask you this, 7th graders. How many numbers are between 2 and 3? Or 0 and 1? Or 10 and 11? Or any number and that number plus 1? So when we use any number, get ready for this in algebra next year. We have pre-algebra. When we don't care what number we're talking about or it doesn't matter, we'll say a letter. It's called a variable because it can literally be any number. In this instance, I picked 2. But how many numbers are there between some number and the number after? We'll call it r plus 1. Here, 2 is r, 3 is r plus 1. When you see this algebra stuff, we're making it up. We're not saying that 2 is r or anything like that because it could have been any number. And we don't care what the number is or it doesn't matter. And in this case, it's both. I just picked a little piece of the number line. I could have easily put 26 and 27 or 8 and 9 or -4 and -3. Remember, -3 is bigger than -4. We'll go into that probably, I'm sure, later. We did in the 6th grade, and that's why I got to remember this is the first lesson in the 7th grade curriculum. 6th graders got 3 episodes in, so that's why I'm kind of behind here. But the question stands: how many numbers are there between 2 and 3? Well, I mean, for starters, we can say okay, let's do 2.01. It's $2.01, right? Okay, well then we could do 2.001 and 2.0001 and 2.000001 and then 2.0.01. And we haven't even changed the number to 2, let alone 9 yet. We can add an infinite number of zeros in here and never stop. So there is yet another type of infinity. So infinity, while you think it settles numeric arguments, it actually leaves much to be desired because it's not a tangible, tactile number. Can't just nail it down. Infinity, 8, 2 different things. And the thing with numbers is, although there's only 10 digits, 0 to 9, you can put them together in an unholy amount of ways here. So, there's yet another type of infinity. The number of decimals between any 2 numbers. So, while that's the case, it's kind of mind-boggling. These things get kind of big really quick. So there's another type of number in the rational box. I kind of want to show it to you. Again, the 6th graders saw it in a lesson. It's a decimal, but it's a decimal that repeats, and it does not end. And there's a couple of ways to do it. Quite easily is to take any digit between 1 through 8 and divide it by 9. That answer is 0.444. I think you get the drift. Now, to make that easier, what we do here is say 0.4 with the little hat over it. That line over it means that number repeats forever. And we've been in the first lesson, we kind of bit off a lot here, but I'm going to try to explain this forever here. 4 divided by 9 is a rational number. The answer to 4 divided by 9 is a rational number. The 0.4444444. So we put a little hat or put a line over the number 4 to show you that it repeats forever. And by forever, I mean if you use every pencil, pen, crayon, marker, paintbrush, chalk, stick on dirt, anything you can use to write with that has ever been, that is now, or will be into the future, any holographic way of writing anything to keep writing these 4s, it is still not enough. That's what I mean by forever. This goes on and on and on and on forever. And I'm going to pull out some little math minutes, and I'm thinking about in one of these doing something to show you how division works. And you'll see that that in a situation like this decimal will go on and on and on forever. So a decimal that repeats and does not end is a rational number. Another example of one is my favorite number. I'm going to tell you about it right now. The number 14285 I know, another big number. This is what you get when you divide by 7. So I'm going to pick a number between 1 and 7. Let's say 5. I take 5 and divide it by 7. That is a 7, believe it or not. The answer is 0.71428. And this whole thing repeats. So instead of writing 71428 again and again and again until we run out of everything to write with, we're going to put a line over 71428. Look at your calculators, put in 5 divided by 7. That is a rational number. Any answer to a division problem, and like my students know in the 6th and 7th grade class I taught in the last year, every fraction is a division problem. Top number divided by bottom number. Now, in this case, like the 4 divided by 9, the 4 repeats forever. But in this case, we have more than one digit that repeats forever. 5 divided by 7 is 0.714285,714. And you can see how the numbers shifted to this, and then 7.14285,7.14285,7. Now, we multiply 142,857 times 7, you get 999,999. Kind of a weird number. But over the course of the series, I'm going to show you numbers that, could be displayed. That's from Dirk Niblick. But some numbers are really awesome. And you may have had your feelings about math, felt some kind of way about it. But you never know that, some numbers are pretty cool. And one of the first numbers that is cool is 142,857. Anywho, now, the cyan box, what's that all about? The cyan box contains basically one type of number here. It's a decimal, but notice that it isn't outside of the other color boxes. It's off to itself, which means that none of the numbers in the black, orange, green, or blue box are contained in this cyan colored box. Repeat. None of the numbers in the black box, the orange box, the green box, or the blue box are contained in the cyan box. The type of numbers that are in this box are numbers like pi and e and the square root of 2. These numbers are irrational. And if you think about it like in an uber sad scenario, you may have been called irrational. You're being irrational. Well, they're saying you're being crazy. And these numbers are crazy. Pi is the measurement of the inside of a circle to the circle itself. This number is admittedly easily 22 divided by 7, but it gets more and more than that. 3.141596, blah, blah, blah. Now, E is a measurement in super duper calculus. I won't get into it. And all I know of it is that it's 2.787, I believe. And it goes on and on forever. And square root of 2, we'll get into square roots later. The square root, the funky looking division sign, when you see that, that says what number do you multiply by itself, and there's usually a 2 right there. 2, which is how many times you multiply. There'll be a number right here. If you don't see a number, it's 2. So what number do you multiply by itself 2 times to get 2? I know what you're thinking, and it's not 1, because 1 times 1 is 1. I didn't say add, it said multiply. So the square root of 2 breaks down to 1.414, blah, blah, blah. These are decimals that do not repeat, like 0.444444444, remember that? And these are decimals that do not repeat, and they do not end. I was trying to draw a decimal. They do not repeat, and they do not end. So we know 1 times 1 is 1. 1.4 times 1.4 is 1.96. 1.41 times 1.41 gets you a little bit closer to 2. And 1.414 times 1.414, again, you're doing it twice because this sign says, again, there's a number right there. And if you don't see a number there, it's 2. What number do you multiply 2 times to get the number up under there? That's weird. In this case, it is 2. The number we're trying to find is 2. So what number do you multiply by itself, or you multiply 2 times to get 2? The more this number you use, the closer you get to 2. The sad thing is, it will never get to 2. So you keep going, keep going, and keep going. 22 divided by 7 is 3.14, on and on and on, but the division never terminates. Same thing with E here. Now, these numbers are irrational because, unlike 4.5, right? You can put a 0 there, but you kind of don't have to. That's a placeholder. It stops. 0.75 stops. 3 stops. 0.444 does not stop, but it keeps repeating. It repeats on and on and on. 0.444. That 0.142857, when you divide by 7, that whole series of numbers repeats. 142,857, 142,857. So, that's an irrational number. And these are the numbers that you're going to be dealing with in this class. From counting to whole, where we just added 0, to integer, where we added the negative numbers, to rational, where we added decimals that do repeat and don't end, or that actually end, like these two here. So, that being the case, let's take a look here at the next slide, which isn't that one. Where's that? Okay. Let's compare some of those numbers. And I brought in the number line here, and we can look at it and try to compare some of these numbers. So, remember, on this number line, or I might be too big. As you go to the right, the numbers get bigger. And I know at the social intelligence 0, 1, 2, 3, 4, 5, the numbers are getting bigger. But that also means you're adding. And as you're going to the left, the numbers are getting smaller. That means you're subtracting. So while it looks like a 10 and 5, that's not a 10 and 5. 10 is over here. 5 is over here. This is negative 10 and negative 5. And negative 10 is smaller than negative 5. And negative 5 is smaller than 0. I know that's weird, but would you rather owe me $5 or would you rather be broke? Would you rather owe me $10 or owe me 5? Well, the correct answer to that question is the bigger number. Obviously, 0 is less than 5, 5 is less than 10, 10 is less than 15. So as you're going this way, the numbers are getting smaller. You can even say you're subtracting. But as you're going this way, the numbers are getting bigger, and you can say you're adding. And we'll probably get into probably get into adding integers here, I'm sure, at some point. That's actually what sixth graders started with. But let's just identify these numbers on the number line. So let's see. Get rid of these less than symbols. Oh, and let me tell you the symbols. This symbol is less than. This symbol is greater than. If you want to look at an example, my second grade math teacher told me that that is an alligator's mouth, and it is always hungry, and that mouth is always open to the larger number. So in this case, the alligator's mouth is going to be open to 10 because it's bigger than 5. In this case, the alligator's mouth is going to be open to negative 20 because it is bigger than negative 25. Just something in case you got mixed up with those. So let's identify 17. I'm sure we can find that. That's 2 past 15. We can identify 15.5. Now, see here, here's 2 and 3. Here's just a few of the numbers, like I said, between 2 and 3. There's many, many more, but we just broke it up into quarters. There's 1 quarter, 1/2, 3/4, and the next whole number. So we can kind of split the difference here between 15 and 16 and put a little slash right there for 15.5. Okay, 8, we know is right there. 3 past 5, 2 before 10. Negative 3 is 3 left of 0 and 2 right of negative 5. Negative 11.5, there's negative 9, negative 10, negative 11. I kind of got that out here, but it'd be right in between these two lines here, negative 11.5. Draw a line out there, negative 11.5. Yep. And negative 23.5, way out yonder. Negative 20, negative. How's that happening? That's weird. So negative 20, negative 21, negative 22, negative 23, negative 23.5. There we are. Let's go. If you have a 0.5, just put it between the two numbers there. Now, we've got another group of numbers like that, but we're going to put them in order from least to greatest. And remember, the numbers that's furthest to the left is the least. So the biggest negative number is the smallest number. So let's start with that one. Looks like, oh, negative 29. That is the least. And then let's see what's the next number. Negative 22. Okay, it's right there. Okay. It's bigger than negative 29, right? But still pretty small. Next number is, we have 4, 1, 17, and 8. So the next number is 1. The next biggest number is 1. And then 4. And then 8. And then 17. That's how you put them in order from least to greatest. Negative 29, negative 22, 1, 4 is actually the fourth one. 8 is fifth. And the biggest number in that group is 17. Okay. Now, this was just to show you that there's numbers in between numbers. You could also do it as a fraction, but 1 over 4 equals 0.25, 1/4, right? 0.5 is equal to 1/2. 2.75 is 2 3/4. We got broken up by 4. You can kind of think of the Kit Kat bar. Each one of those is 0.25 or 1/4. And now, again, here, when we're comparing integers, the number to the right is the bigger number. So I'm going to clear out the lines here so we can post these and you can see what we got going here. I throw the number line, we'll get rid of them. So we have 3 right here. We have -4 right there. Well, 3 is to the right, so 3 is bigger. I got 5 4/7 and 5 7/8. Now, both of these numbers are bigger than 5, but smaller than 6. So we can zoom into this here. We can just say this is 5, this is 6. Now, 4 divided by 7 is 0.571428. Remember, divided by 7 is weird. 0.57142857142857. Now, 5 divided by 8 is 0.625. Which is about right there, 0.625. So, as long as they're not negative, and they're not, this is a bigger number. If we were doing -5 over 5 over 8 to -5 4 over 7, this would be the bigger number because it's closer to 0. Over here on this side of town, on the negative side of town, I'm not trying to be negative, but on this side of the tracks, the number closest to 0 is bigger. Now, on this side of the tracks, the number closest to 0 is smaller. That's how powerful 0 is. When we deal with negative numbers, the number closest to 0 is bigger. You wouldn't want to owe me $20. You'd rather not have any money at all than to have to give it to me. And that's what all the red numbers are. But conversely, over here, you'd much rather have $20 than to be broke. All right. So we got -3 and 2. We got -3 right here. We got 2 right there. 2 is to the right, so 2 is bigger. Now, here we are, -8.4, -8.8. Okay. Oh, hey now. A little too much there. A little bit more. There you go. Now, so now we have -9 right here. And right here we got -8. Remember, -8 is bigger. We're looking at this right here. These two lines right here zoomed in. Okay, that's what this is. -8 is this line. -9 is this line. So we have -8.4. This would be 0.25. This would be 0.5. Be 0.75. So ignore all this down here. This is only when it's positive. Now it's negative. It goes like this. So we have -8.4. So it's 2, 5, and 5. So -8.4 would be right there. And we have -8.8, which is past 0.75, but not quite there. So it's about right here. -8.8. And remember, the rule is the number closest to 0 is the bigger number. So -8.4, which is right here, -8.8, which is right there, -8.4 is closer to 0, so it's the bigger number. Now, I know that doesn't look right, but I'll say it like this. If you take the negative signs off, we all know that 8.8 is bigger than 8.4, right? So, the rules change when you're dealing with negative numbers. So, 7th grade, that's about all I got for you there. We're able to classify and list numbers, and now you know a lot more about infinity than you thought you would, and how there are different types of infinities. And all those numbers in those green and orange and blue and black and cyan boxes are what we're going to be going over the course of this year. So hopefully you took notes, and if not, you can come back and watch it again. Email me if you need to. I'd be more than happy to help you out with it. All right, so that's the first couple of standards for the seventh grade curriculum. We were able to identify numbers and to put most, if not all of them, into one of five different boxes. Don't worry, seventh graders, you won't have to worry about that cyan colored box, the irrational numbers, until your Algebra 1, Algebra 2 days. Um, the first few videos I did was for the sixth graders. I think now I'm going to start going in a cycle of sixth, seventh, eighth, then Algebra 1, Geometry, Algebra 2, round and round and round. So there'll be a new grade every video, and when you're starting your middle school or high school career, you'll be good to go. So no matter which grade you're starting, there's be some content coming up for you very soon. I'll try to put something out at least every day. And I'm thinking about doing some little things with with minute videos or something like that, maybe some shorts. We'll see how it goes. I don't have Snapchat or TikTok or anything to make the little videos or a quicker way to get in touch with me by phone. Email is the best way. If you have any questions, I'd be happy to help you out with your work, whatever you're going over, or if you want to go over something in the videos. Be reached. I have an email right here at bearsfan813 at yahoo.com. Bearsfan813 at yahoo.com. Bears fan because I am a Bears fan, if you haven't noticed. And the 813 is my grandma's address and my birthday. So just seemed right. Um, yeah, so eighth grade will probably be coming up next, the first couple for eighth grade, and then Algebra 1, Geometry, Algebra 2, and then back to sixth grade, seventh, eighth, on and on and on. But no matter which grade you're in, there's help available for you. And I'll be more than willing to help and lend my time and talents to help you get better at the subject. And no matter what grade you're in, you can do it. You may not know that you can do it. You may not have even done it, but you can do it. And if you need help, I'll be here to help you. And no matter what grade you're in, math matters. It really does. See you in the next one.